Hello everyone. In this video we're going to cover categories in which we can place our algorithms. We've already seen a lot of these categories, but I'd like to finish up an algorithms course by just taking a look at these categories directly, making sure that we understand how algorithms would be placed into these different categories, and also to see a few other topics or algorithms that didn't show up in class here at the end of class. So we'll see a few new algorithms that are kind of similar to other algorithms we may have seen before, at least in the basic way in which they go about solving their problems, so the strategy. So in this video, we're going to cover a few of these, not the entire slides have been provided. We're going to start off, we're going to talk about brute force algorithms and then greedy algorithms, and then we'll cut the video short and probably cover the rest of this in class. So let's see if we can load this up, and I'll see if I can make my pointer appear here. And let's see if we can work through these slides. So this is a larger set of topics. I said we're going to cover these first two, brute force and greedy. I also like to cover divide and conquer, decrease and conquer, and transform and conquer, which are three other categories. I'm just calling that star and conquer or wildcard and conquer here. We will not cover those in the video. We won't cover dynamic programming. We won't cover backtracking. These are all very interesting, but I want to keep this video as short as possible. Alrighty, so brute force algorithms. This is a very simple approach. Usually you take a problem and its problem statement and you begin exhaustively searching for an answer to a problem. So here, for example, I talk about the password cracking problem. So one way, not a great way, to try to break someone's password is just to enumerate over all the possible passwords, generating every possible combination of characters that could be typed of a certain length, and then comparing that against your password to see if they have essentially figured out what your password is. Now, obviously, that's a lot of work, and most of these brute force algorithms do fall into that category where there's a lot of work that needs to be done. These are usually bad ways to go about solving problems, although it turns out that for certain types of problems, this is really the best type of solution that we know, at least currently, and we'll see that shortly. So what have we already seen that uses brute force? Well, this makes sense with password cracking. We've seen linear search, where we just search through an entire array. We don't try to do anything fancy. We don't try to sort the elements in an array if they're sortable. We don't try to take anything into account about what we know about that input array. We just say, hey, we don't know anything about it, so we're going to go ahead and search through every element in the array. Obviously, if there are millions of elements in that array, it's a lot of work that needs to be done, and this brute force algorithm is going to go ahead and do that. And then I want to show you a very famous problem called the traveling salesman problem. You may have heard this before, abbreviated as TSP, or the TSP problem. This is a very famous problem that has notoriety for being very difficult to solve. It's difficult to solve, it's difficult to prove that a solution is actually a solution. Pretty much everything about this problem is just difficult. And so let's see if we can dive in with the definition of the problem. So in the traveling salesman problem, you're given a group of cities, let's say they're n cities, and you're given a distance between each pair of cities. So I know the distance, so give me any of those two cities and I can tell you how far apart they are, maybe in miles. And then your job is to give or to calculate the shortest route that a salesman would take to travel to each of the cities and back to their original starting city. So, and when I say shortest route, I mean we want to have covered the least distance. And you'll notice here on the right, we have a graph, and I'm modeling this as a graph or a weighted graph. Here the vertices represent a city, so this is city A, city B, city C, and you'll notice that I have all possible edges present in my graph, which abides by that definition of the problem where it said we know the distance between all cities. So each of these edges represents the distance between a city. So the distance between A and B is 10, the distance between A and E is 31 here. And hopefully I don't have a typo here. I had to put that graph together. And if you see one there, well, bear with me. But we have a distance between each of those cities. We want the salesman to visit all of them, A through H, using some of the edges in the graph. And we want the total cost of the route that was taken to be minimal. So I'm going to pick edges and travel from city to city to city in some order, and the total cost of all of those edges should be minimal. And then at the very end, that the salesman will return back to the starting city. Let's say we started at A, and we want to identify what that shortest path would be. All right, so this is actually another way to look at a graph where we're trying to find what's called a Hamiltonian cycle. And that Hamiltonian cycle needs to have a minimal distance. So what's a Hamiltonian cycle? That's a cycle in your graph. Here you can see I have a cycle A to B, B to E, D, C, G, F, H, and A. And this cycle can only pass through a vertex exactly once. So for example here, if I went from A to B, B to E, E to D, I couldn't travel back to B and then over to H. I can only visit the vertex exactly once. And you'll notice that if we follow that rule, and that cycle has the minimum cost of all the edges throughout the cycle, then that's actually the same as giving a solution to the traveling salesman problem. And you'll notice here I've given a solution. Notice I've highlighted these edges. But to be honest, how do we know that that's actually a solution? I mean, you could look here in the background and say, okay, the numbers for the edges that I didn't choose are roughly speaking larger than the edges that I did choose. But you could imagine that there could be lower numbers here, and it may be difficult to figure out whether we took the right route, right? Should we have picked 20 here? Should I have picked 19 here? I'm not sure. Even if you're handed a solution to this problem, it's incredibly difficult to even determine if that is the correct solution or a correct solution, because you would have to look over all the possible cycles in the graph to even determine whether that was the best cycle. And there are lots and lots of cycles in this graph, as we'll see here in a moment. So we're looking for this thing called the Hamiltonian cycle. It's very close to what's called an Euler cycle. I always call this Euler. If I change from Euler to Euler, bear with me in the video. An Euler cycle. And an Euler cycle is a cycle in the graph, but the Euler cycle only passes over each edge exactly once and then returns back to the original vertex. So either we're going to limit the edges to visit exactly once, or the vertices. They sound very similar, but they are different. So here, if I went from A to B, I couldn't travel back from B to A and travel across that edge again. Whereas with the Hamiltonian, I can go A, B, B, E, D. I could not go DB back to B with a Hamiltonian cycle, but I could do that with an Euler cycle. Okay, so that's the problem. I said it's difficult to determine an answer, and even when you have an answer to the problem or solution to the problem, it's difficult to even determine if it's correct or not. So how much work would go into this? Well, we're talking about brute force algorithms, so a brute force solution would be to exhaustively search in this graph. So the first thing we would do is we would pick from the n starting cities. So I would pick one of these cities and I would try them each out once as the starting city. So I have n choices if I have n cities. The next thing I'm going to do is I'm going to pick from among n minus 1 neighbors. So remember, this is a complete graph. All the possible edges in the graph are there, which means that this vertex is connected to all other n minus 1 vertices. In which case, I can choose any of these paths to start out in my circuit through this graph. So I started out, I had n choices for a starting city, n minus 1 choices for the next city to visit when I jump across this edge or this edge and I move from city to city. After I visit the next city, let's say I happen to go from A to H, then I have n minus 2 cities that remain. I can't go back to A, and I'm already at H, so I can traverse to one of the remaining cities. So I started out with n choices, then n minus 1, now n minus 2. When I go to the next city, let's say I went from H to F here, I would have n minus 3 choices, and so forth and so on. It turns out to actually generate a solution here using that exhaustive approach, or even to look through all those choices. Well, you start off with n, and then you have n minus 1 and then n minus 2 all the way down to one choice. That last choice would be just moving back to the starting city. And this represents a factorial number of paths that can be taken in the graph, or there's a factorial number of solutions to the traveling salesman problem. This is astronomical. If you have even very small n, this number is prohibitively large. So difficult to solve problem. There are a few other solutions to the traveling salesman problem that may improve upon this a little bit, but they don't get below exponential running time. Once again, this is a very hard to solve problem. We don't know an efficient way to solve this problem as it stands right now. Okay, greedy algorithms. So this is a new category. We just talked about brute force. We can do better than that. That's usually, I can't really think of any algorithm where brute force is the way we want to go. We've seen a few greedy algorithms. In this technique, you're always trying to make the best choice from among the possible choices at each stage of an algorithm. So let's say your algorithm's been running for a bit, and we just paused it for a moment, and your code inspects the situation during the algorithm. It would always attempt at that point to make the next best choice, or the best choice given the data and the state of your program. And we've seen some of these algorithms before. Dijkstra's algorithm for shortest paths, that's a greedy algorithm. In Dijkstra's algorithm, we were sorting our vertices based on their labels, and we would always pick the best label with the lowest value as part of the algorithm. Prim's minimum spanning tree is very similar as well, where we're greedily selecting vertices or edges. Same with Kruskal's minimum spanning tree algorithm. With Kruskal's algorithm, I can't speak. With Kruskal's algorithm, that's very easy to understand. When that was the one where we would just pick the minimum edge, very greedily, just pick the best one, unless we would create a cycle in our graph. So I'm assuming you're familiar with these. But those are all examples of greedy algorithms. Here I mentioned the fact that greedy algorithms can often produce incorrect results. Being very short-sighted and looking at what's just in front of you at any one moment and not trying to plan for the future will often get you bad results in any algorithm, but it turns out these first three are examples of algorithms that give you good results with good running times. If you remember, all of these pretty much ran in linear arithmetic time, and that is using the greedy strategy. So as part of these slides, I would like to show you a few more algorithms, the Huffman encoding algorithm and a coin changing problem. The Huffman encoding algorithm is just an interesting new algorithm that shows off how greedy thinking can produce an interesting result. And then the coin change problem, I put that in here to show you an algorithm that, for example, sometimes produces an incorrect result. So let's take a look at these. All right, so Huffman encoding. Put on your thinking caps. This one can be a little challenging to kind of wrap your mind around. It's a greedy algorithm, so it's going to try to make the next best choice. I'll try to call it out, but in the same sense as I'm describing this algorithm, try to think about what part of it makes it greedy. At what point of the algorithm does it just make the best choice from what it can see at that one moment as your code is executing? What this algorithm does is it provides an encoding for text to binary. So we know that your computer looks at everything as numbers in binary. We often convert our text-based characters to binary using an encoding. You may have heard of ASCII or Unicode or UTF-8. These are all very familiar encodings. These are mappings between text characters and their binary equivalents, and where they'll be stored in memory. And so we do that because that's what a computer understands, but also we're challenged with figuring out how to efficiently store characters in a program as numbers, and then also how to be able to represent enough of the characters that exist out there. There are lots of languages in the world, and how can we be efficient, or how can we optimize how we're storing these characters, since there are so many from different languages that we'll need to store inside of our program. All right, the difference here is we've seen these encodings. We know what, I'm hoping you know what ASCII is in Unicode and these encodings. Huffman encoding, what it does is it takes a look at your string and tries to identify characters that are showing up more often than others. And if we see a character that's showing up more often than others, we're going to try to optimize that character in the way that we store it. So here I could look at my source text here, and you'll notice that the letter E shows up a bunch of times here, as well as the letter R, and then everything else pretty much shows up once, maybe twice. I guess the space character shows up twice as well. So what we would want to do in the Huffman encoding is use less bits. Notice here I give the number, the binary equivalent of these characters, and notice the one that shows up more often than the others takes less binary digits to store it. Same with with R, or this is not underscore, that's the space, but R and the space take less binary digits using Huffman encoding than the rest of the encoded values here. So we want to look at those characters that show up more often, use less binary digits to store them, and by doing that, since they show up more often, we're going to have some compounded savings where every time I store E, it will take less binary digits. And you'll see, even just from a glance, that this is much shorter than what you're seeing over here. And this can get even longer. They're not always going to be this short. Sometimes they may get close to this, but you're usually going to see a saving using a compression algorithm like Huffman encoding. So let's take a look, see how this is done. I've got the algorithm here on the left. Don't get intimidated by this wall of text. On the right side, I'm going to have some trees that are going to be drawn here as part of the algorithm, and they're hopefully going to give us a visualization of how this thing behaves. So in this algorithm, we store tree nodes, similar to the tree nodes you've seen in binary trees or maybe in a heap-based structure. And we're going to call these Huffman nodes. The nodes in this tree are called Huffman nodes. And each node is going to store a character and a frequency. So here I have A in one of my nodes, and we're saying here that A shows up 20% of the time. Here V shows up 5% of the time, represented by this Huffman node. R 30% and E 45% of the time. So we have a character and a frequency. So the very first part of what we need to do is we need to take some source text and we need to inspect it, figure out the frequency of the characters in that text, and that's going to guide the algorithm, meaning this compression is specific to the text that it's reading. So for example, here if I used a little bit of text here, I may be able to get a certain amount of savings. If I used a larger file, maybe the effect will be more or less depending on how many bits are saved. It depends on what the text looks like. And the more repeated characters you have in your text, the more savings we're going to have as part of this algorithm. So what we do as part of this algorithm is I go through and I inspect every character. And I count the number of times it shows up in that string. I record those frequencies. And then I create a bunch of Huffman nodes, one for each character, with the character and the frequency here. And you'll notice that I have those for our source string here. And I'm going to place those in a priority queue. And the priority queue is going to sort those based on the frequency or the percentage, and we're going to pull out the minimum frequency at each step. So here I would pull out 0.083 before I pull out 0.333 because this is a smaller value. So we'll place those all into a priority queue. And here's where it gets a little challenging. We're going to pull out two of those at a time, because we're going to try to assemble a binary tree. And the shape of that binary tree is going to help us determine what the binary equivalent of a character should be using this encoding. So what we'll do is we'll pull out the two smallest elements from the priority queue. So if I come back here, that would be H and W. I could also choose A and exclamation here. These are all the same, but I'm just going to pick out two here visually. So I'll pull those two out. And I'm going to create a new Huffman node, a parent node for those two nodes. And this is going to point its left child and right child to those two Huffman nodes. And in this parent node, I'm going to put the sum of the frequencies of the child element. So here, this is showing up roughly 8% of the time, roughly 8% of the time. Here, together, these characters show up 16% of the time. So I'll place these as children in a new node, and then I'm going to take that new node and place that back into my heap, where it will be placed in the correct order so it can be pulled out as the minimum value at some later point. Notice down below here I show the heap after I place that new parent node into the heap. Now a couple things here. H and W are not part of the heap or the priority queue at this point. Let me say that again. H and W are not directly in the priority queue. This parent node is in that queue. And that's why I've kind of grayed these out a little bit so that they kind of fade into the background. Don't get me wrong, this node that's in the queue references these as child elements, but we're going to make all decisions in the queue based on the parent value and whatever other elements are in here. These child nodes are just tagging along as part of this algorithm. Okay, so I said we pulled out two elements. We created a new parent node with those two elements as child nodes, and then we'll place that back into the heap. We're going to continue to do this over and over and over, pulling out the two minimum elements, creating a new parent, placing it back into the priority queue until only one element remains in our queue. And once one element remains in our queue, that will be the root of our Huffman tree, and we're going to use that to show the compression of our characters here. So I'm going to pull out the next two smallest elements from that priority queue. If I come back here a step, that's A and exclamation. I'll pull those two out, create a new parent, place those back into the heap. Now you'll notice here, once again, the parent node is all that's in the heap. These child nodes are just tagging along as we go along. Once again, then I'll take out two of the next minimum elements, and I've got four to choose from. I'll take out, I think, R and space here, and I will give those a new parent. Notice our frequencies are going up here. Now the parent node has 33%. You'll also notice that the number of elements inside of this priority queue is getting shorter. So eventually we'll only have one element in this priority queue, after which we'll have our tree. So here I'll join R and space together and place them back into the tree. Notice all the child nodes here tagging along. We've got four nodes left in our priority queue. I will pull out these two at this point. Notice these don't have characters, and that's one of the key takeaways from this algorithm is you got to be a little careful. Some of your nodes have characters, some don't. So these all don't have characters, but we can still join these together with a new parent node, and I'm going to do that. So here I pull out 16%, 16%. I add a new node with the sum of their frequencies, and I'm going to place this back into the heap. You'll notice also when I join these together that this is starting to look like a binary tree. So we are building a tree here based on these frequencies. And we'll talk about why in a moment, but let's just work on the mechanics. So I'm going to continue to do this. So afterwards, my heap looks like this. So I have one tree rooted at 33%, another tree rooted at 33%, and then a single element at 33%. I think on the next step I join these two together. It's hard to fit it all in one slide. It looks like I did. Here I have roughly 67%. I've joined these two trees together with a new parent node. I'll place that back into my heap. Now I have two choices left, minimum, minimum, and I'm going to join these two together with a common parent element. You'll notice that this is very close to 100% or 1.0, and that's the way the algorithm works. You'll get some rounding error here, especially when you're using double values in a language like Java or C# or pretty much any language these days. The double values usually have round off error, and you'll see that here, and I'm trying to represent that in my code as well. So if you do work with Huffman trees at all, and you notice that this is very close to 1.0, but not quite, don't be thrown off by that. That's all right. You're still going to get some good savings here using this encoding. So I'll join this together. At this point then, I have one element in my heap, and we have our Huffman tree, as we can see here in the slides. The next step is I want to use this tree to generate the binary value that's going to represent each of the characters in our string. And just a reminder, that binary value should take into account how often a character shows up in that string. So you'll notice here that E is closer to the top of my tree, and if you remember, E showed up most often. In fact, R and the space character showed up right after that. That's the second most often in that string. And you'll notice that these are up higher in the tree than some other elements near the bottom. These elements near the bottom showed up the least amount in that tree. So what we're going to do to generate these binary strings is we're going to have a simple rule here. We're going to traverse our tree, and every time we go left down the tree, we're going to pick one of the binary digit possibilities. So in this case, when we go left, I'm going to pick 1, just arbitrarily. And if I ever end up going right, I'm going to pick binary 0. And as I go left, right down the tree, searching for an element, let's say it's W here, I'm going to concatenate those values onto one another, building up a binary string that will eventually represent our value here. So here I'll start at the root, I'll go left and I'll add binary 1. When I go left again, we said every time we go left we'll add 1. I'm going to add this second 1 to the end of my binary string. I go left again, I'll add another 1 to the right side of my binary string. When I go to the right, I'm going to add 0, and here we get 0 to the right of our binary string. And what we're going to do is we're going to do a traversal of this tree, so we visit each of the elements, and we're going to keep track of those strings as we go along. And every time we see a character in the tree, we are going to record that binary value, and that will be the associated encoding for each of those strings. So here's what the tree would look like afterwards. So here, if I go left, this is 1. Notice there's no character here, so we don't care about what the binary value is stored inside that node or associated with that node. If I went right, though, you'll notice we get 0 from going right, and we immediately have one character that's used to represent E. And if you remember, looking back, I've got the encoding here. It looks like I've got a bit of a typo here, but that's right. But if you look back at these encodings that we saw at the very beginning of this topic, you'll see that that E has a very short number of binary digits, and it shows up most often inside of that string. So the fact that this is going to show up often but take the least amount of binary digits to store in memory is savings. We're actually reducing the amount of space required to store this string because we're taking into account the frequency of its characters. And then I'll walk you through a few more of these. Let's say I wanted to know, how did I get 1, 0, 1 here for the binary equivalent of R? I went to left 1, to the right 0, to the left 1, so 1, 0, 1. Similarly, I could go for the exclamation here, go to the left, to the left, to the right, 1, 1, 0, 0. And all we would do a traversal of this tree using a common traversal, like in orders traversal, pre-order, post-order. Just pick one of those, and as you're moving throughout the tree, you're just going to, every time you go to the left, you'll keep track of this binary string with a 1, and if you go to the right, you'll add 0 to that binary string. Once we then have each of these characters mapped to its binary equivalent, we can then represent those characters using these shorter values. And this is unique to this string and is going to give us savings here, as you can see in this next slide. So here I've shown you, let's assume we use ASCII, which is not very popular these days. We usually use extensions of it. You'll typically see some version of Unicode these days, but let's assume that we're using ASCII codes, which can represent, have 8 bits to represent characters. It's a limited character set. But here, if I used all of these characters here, and I'm only using 7 of these, so I'm using the more restricted ASCII character set, that to represent here we are took 96 bits, because each of these are fixed length binary strings. Whereas if I apply my Huffman encoding, you'll notice the savings that we're getting here. Here is the letter E at each of the positions inside of my string, which is using only one character for one binary, one binary digit for each. And you'll notice that we went from 96 bits all the way down to 32. Now you won't always see as drastic of a difference as you're seeing here, but hopefully this gives you an idea of how we can kind of use this encoding and take advantage of the structure of our data so that we can reduce the amount of space required to store that data. Alrighty, at this point, I would strongly suggest practicing this algorithm. You've got it in video form now. You can go back and watch my example here. I've given you a new string to work with, and what I'd like you to do is practice using the Huffman encoding algorithm with this string. And what I'd like you to do is, I've given you the ASCII code characters over here. Your job is to use the Huffman encoding algorithm to generate the Huffman values, and then to see how much space it would take to store "Are we there yet?" in ASCII, as opposed to how much space would it take to store it using the Huffman encoding. So what you'll do is you'll determine the frequency of each of the characters here. So notice once again E shows up several times, T shows up a few times, things like that. and you'll calculate the frequencies, you'll create your Huffman tree nodes, you'll assemble the tree using your priority queue, and then determine those binary values. So my suggestion is pause the video right now, practice this, and show that you kind of are following along. If as part of the algorithm you get stuck at a point, you can always go back in the video and kind of see what I did, and hopefully bridge that gap between what you saw before and what you're trying to do now. Okay. Alrighty, I'm going to show you one other problem here, and then I'm going to end the video. Like I said, I just wanted to cover the brute force algorithms and the greedy algorithms. This is another interesting algorithm. In fact, when you're talking about types of algorithms, there's actually a lot of coin problems that are pretty much all of them are interesting in one form or another, showing off different ways we can approach a problem. I'm going to show you a greedy coin problem, and this is all about how do you give change back to a person. In let's say you were working a register and you had to give people change, right? How do you get them back their change? So for this, what we're going to assume is we have a certain type or set of coin denominations. So here I'm assuming we're using some coins. Coins differ country to country, so let's not make any assumptions that these are just American coins. This algorithm should work for any set of denominations. But given some coin denominations and an amount n, this problem is going to answer what is the minimum number of coins required to make the value n. So we know the value n. So I could say the value is 76. What's the minimum number of coins that it would take me to give you the value 76 using some types of coins? So the greedy solution is going to work like this. We're going to store a temporary variable. It's going to hold our value n. And we're going to count coins with a variable called c. And we're going to continue until our temporary variable is 0. We're going to reduce our value n over and over and over in a greedy way and try to make the best choice possible each step. And of course, the greedy approach would say, well, pick the best choice in my current situation. So what we're going to do is we're going to always take the largest coin that's part of our denominations, and we're going to give that coin to the person and reduce our total amount that we owe that person by that largest coin. Once we've done that, we're going to reduce our value, we'll increment the number of coins that we've used to keep track, and then we'll reduce our temporary variable by that amount, and we'll continue until nothing is left. Now, this is some kind of high-level pseudocode. Let me show you what this would look like. It's not so hard to do. So let's assume we want to get the value 89, and that we're using American denominations just for this argument. Once again, this works for other denominations. Let's say you have, penny, nickel, dime, quarter, and 50-cent piece. So I'm going to start off, and I'm always going to pick the largest coin, like I said before, which is the greedy approach. So I owe somebody 89 cents, so I'm going to hand them a 50-cent piece. I now owe them 39 cents. That's what I'm showing here as we move down this list. And I handed them one coin in the parentheses here. That's the number of coins that I've used. Next, I can't hand them a 50-cent piece because I only owe them 39 cents. So I pick the next largest coin that's smaller than this, which is a quarter. I'll hand them a quarter. That's my second coin I've handed them, and I now owe them 14 cents. I'll give them the largest coin smaller than that, which is a dime, my third coin. I owe them 4 cents, and then I'll hand them a penny, a penny, a penny, and a penny, and eventually I will have given them everything I owe them. But at each step, I chose the largest coin possible, and I was able to determine that the minimum amount of coins needed was 7 in this case. And if you're dealing with American coins, this greedy algorithm basically works. Okay, a few other examples I have here use other denominations, some bizarre ones, and I'm just picking numbers kind of randomly or in some sort of interesting way here. Here I picked all odd numbers, and here I picked just some just kind of numbers here and there to show you how basically this would work. So let's say I had these denominations and I owed 31 cents. I would give them a 9-cent piece, 9 value from some coin, right? This would be 999, that's 27. I still owe them 4, in which case I would take the next highest coin, which is 3, and 1, and eventually that would take 5 coins. Here, once again, I'll give 15, 15, 15, 15, that's 60. using the largest denomination, and then the next largest, if I have 7 left, would be 4, and then 2, and then 1 for 7 coins. So this shows you some different looking denominations from what you may be used to. I ask you a question here though. I say, hey, can you think of a set of denominations where this algorithm doesn't produce the right result? I mentioned that before, that these algorithms, greedy algorithms, are short-sighted. They'll often produce incorrect results because they're not looking towards the future. And it turns out you can do this. And I've given an example here. You can come up with different ones. So here I want to get the value 33. With these denominations, if I take the greedy approach, I always pick the largest coin first. So I would pick 15 and then 15. I would owe them 3 after that, and I'd pick a 1 piece, a 1 piece, and a 1 piece, and in total it was 5 coins, which is actually an incorrect result. In this case, it would be better to hand them 11, 11, 11, and in 3 coins I actually give them the correct result. So notice I'm not looking ahead. By just taking the best choice possible, it can lead me to an incorrect result, as we're seeing here. And that's something that you should consider when using one of these algorithms. That being said, it's a little bit deceptive because as we've been covering graphs, I've introduced you to a lot of greedy algorithms that happen to be pretty damn good. They work in general, and they're producing good results with good run times. That being said, though, they're not all going to behave that way, and I'm hoping I've convinced you of that at this point. Alrighty, everyone, I'm going to pause here and stop the video, and we'll probably cover the rest of these algorithm technique topics in class. Alrighty, thanks for watching.